Welcome back to Pump Design Lab. In the first episode, we talked about the engineer behind one of the most important pump manuals in our field. In this episode, we're taking the first step into the actual content, fluid dynamic principles. Before we talk about cavitation, impeller design, or pump curves, we need to understand something more basic: how fluids move, gain energy, and lose energy. This chapter is a foundation for everything a centrifugal pump does. Absolute versus relative frames. When you look at a pump, you can describe the flow from two different viewpoints. From the absolute frame, you see the flow as the casing sees it, stationary, watching the fluid move through. From the relative frame, you stand on the impeller blades and watch the fluid move relative to a rotating surface. Pump design constantly switches between these two frames. When we draw velocity triangles on impeller, we're using relative velocities. When we look at the system curve and inlet/outlet conditions, we're usually thinking in absolute terms. If we don't get this frame change right, our understanding of blade loading, head generation, and secondary flows will always feel fuzzy. Conservation equations. Next comes something you've seen many times, but maybe not connected directly to pump design: conservation of mass, energy, and momentum. Conservation of mass tells us that what flows into a controlled volume must flow out or accumulate. In pump language, it controls how flow rate behaves through the impeller, casing, and piping. Conservation of energy is the basis for the energy equation and Bernoulli-type relations. This is where pump head, efficiency, and the relationship between shaft power and fluid energy gain come from. Conservation of momentum links forces to changes in fluid momentum, hydraulic forces on blades, the thrust on the casing, and many vibration problems all trace back to momentum balance. Every time we say this pump develops this much head, or these are the hydraulic forces on impeller, we're using these conservation laws, often without mentioning them explicitly. Boundary layers. Real fluids stick to walls. That's the no-slip condition. Because of this, a thin region forms near every solid surface where velocity goes from zero at the wall to free stream value. This is the boundary layer. Boundary layers generate friction losses along walls. Decide whether flow stays attached or separates in diffusers and volutes. When boundary layers behave well, diffusers and volutes recover pressure efficiently. When they separate, we get losses, noise, sometimes instabilities. So boundary layer behavior is directly linked to pump efficiency and part load performance. Curved streamlines and vortices. In pumps, flow almost never moves in straight lines. Impeller blades, volute casings, elbows, they all force the fluid along curved streamlines. Understanding equilibrium of forces in curve flow and the difference between forced vortices, driven by rotation, and free vortices helps us interpret secondary flows, recirculation zones, and swirl patterns. These effects show up in uneven velocity distributions at the pump outlet, additional hydraulic forces on the impeller, flow non-uniformities that later become vibration or noise, pressure losses. Even a beautifully designed pump lives inside a system that causes pressure losses. This chapter breaks those losses into skin friction, viscous shear along walls, roughness effects, how surface texture increases friction, form drag and vortex dissipation, energy loss in separated regions, tees, bends, and recirculation zones. These losses reduce the effective head of the system and directly influence where the pump operates on its curve, how much margin we have for MPSH, the overall efficiency of the plant, diffusers, jets, profiles, networks. Finally, the chapter touches several specific geometries and phenomena, diffusers that convert velocity into pressure, core elements in many pump designs, submerged jets, which appear in mixing, leakage flows, and erosion-prone regions, non-uniform velocity profiles, especially important on the suction side of pumps, flow distribution in parallel channels and piping networks, which underpin system curves and parallel pump operation. These might look like separate topics, but in the real plant, they all interact with the pump. Link to future sessions. In Pump Design Lab, this Fluid Dynamic Principles chapter is not just theory. It's the toolbox we'll use in every future episode when we later discuss cavitation and MPSH, pump performance curves and duty points, hydraulic forces and vibration, diffuser and volute design. We'll keep coming back to these principles: conservation laws, boundary layers, curved flow, losses, and network behavior. In the next session, we'll start with the conservation equations and connect them directly to pump head, efficiency, and basic performance calculations. If you want to build a solid foundation for centrifugal pump design, stay with this series and let's go step by step.